Hi everyone, welcome to this video where we'll discuss the Spatial SVD model compressions feature in AIMET. My name is Abhi Khobre. I'm from Qualcomm AI Research. AIMET, which stands for AI Model Efficiency Toolkit, is an open source library brought to you by the Qualcomm Innovation Center. So in this video, we will cover how we can use AIMET to perform model compression. And specifically, we will cover the Spatial SVD tensor decomposition technique, and we will also cover how we can do automatic compression ratio selection through a technique called greedy compression ratio selection. I hope you've had a chance to look at the introduction to AIMET video, which is also part of the series. While it is not necessary, I think that video would give you a good background for what we're going to cover in this video. So if you haven't had a chance to look at that yet, I would encourage you to look at that first and then come back to this. Okay, so let's dive in. So here we are looking at the user guide for AIMET, and this is generated out of the source code. So we will specifically look at model compression. So there's a page on model compression. Let's go to that. So model compression is, as the name suggests, it's essentially taking a machine learning model and compressing it, making it either smaller in memory or smaller in compute, meaning reducing the number of multiply accumulates. And then, so you get a compressed model which will run with less latency on target, or would run in more constrained environments. So at a very high level, model compression in AIMET works in the following way. You start with a trained PyTorch or TensorFlow model, and you would take it through AIMET. AIMET is going to produce a compressed model. And we will look at the details of what AIMET does. But this compressed model is just like the model that you passed in. So if you started with a PyTorch model, you get back a PyTorch model. It's a smaller PyTorch model. And you can do with this model everything that you could do with the original model, meaning you could evaluate it, you could train it, you could take it to target. So generally with model compression, it is recommended that we do a little bit of training after compression, and we call this fine tuning. It's just, it's another word for training. So the one difference is that, to train a model from scratch may take 150, 200 epochs. For this particular training, we are talking about the fine tuning. This is a much smaller number of epochs. Generally, we see that we need around 5 to 10 epochs to recover most of the accuracy that has been degraded after compression. I think at the most, beyond 10 epochs, it starts, not having, too much accuracy gains. But I think by 15 or 20 epochs, that should be sufficient. So that's just a guideline. I mean, your model, your mileage may vary with your own model. Okay, so this, let's go back to what AIMET does with compression. So it, at a very high level, there are two steps. So the first step is compression ratio selection. So what we mean by this is, given a compression target, so let's say we want to compress a model to 80% of its original, either in max or memory, right? So either it's 80% of original max or 80% of memory required, and we can choose that. That's a knob that you can pick. We call it the cost metric. So so given that overall target for the model, you would need to decide how much to compress each layer. Okay, so this is what we call compression ratio selection. So this is, at the end of this step, you would know at every layer how much to compress it, if at all. Okay, and then that decision is driven into the model pruning step. And in this pruning step, you would apply like a technique like Spatial SVD, which we are going to cover today. So what I would suggest is we come back to this compression ratio selection. We come back to this part, and we take a look at the model pruning part, specifically the Spatial SVD technique. So Spatial SVD, like we had mentioned in the introductory video, it's a tensor decomposition technique, and in AIMET today it works on convolutional layers. So here's an example. This is a depiction of a convolutional layer, and at the end of the Spatial SVD process, this one convolutional layer would be converted into two smaller convolutional layers. And let me explain why they are smaller. So you start with this convolutional layer, and the way this is shown here is if you think of the input into the convolutional layer, you have some height and width of the image, but then you have sort of channels. And you can think of a convolutional layer in terms of kernel. So generally there's a 3x3 kernel or a 5x5 kernel. In this example, it shows a 5x5 kernel. And so this kernel is what would be convolved over this image. And while this shows the input channels, like it'll do it over the input channels and produce those many output channels. Okay, so if you think about the weight tensor of a convolutional layer, the dimensions, it's a 4-dimensional tensor. It goes from the input channels, in this case 32, to output channels 64 times the kernel height and the kernel width, in this case 5 cos phi. So it's a 4-dimensional tensor of 32 times 64 times 5 cross 5 times 5. Now when the decomposed layers, to decompose the layers, we use this technique called spatial, or essentially Spatial SVD. SVD stands for singular value decomposition. So it's a standard math technique that you may remember. And so since this singular value decomposition technique works on a 2-dimensional tensor, so what we do is we take the 4-dimensional tensor and you flatten it out in a specific way. So you flatten it out such that you have the input channels and one of the kernel dimensions on one side, and the output channels and the other kernel dimension on the other side. And so when you split it, now you're left with 3 different matrices, and in the middle matrix here is the diagonal matrix of singular values. And if you think about it, if you sort these singular values, the lower x singular values are in theory could be thrown out. So we think of depending on how much we want to compress a layer, you could throw out more of those singular values. If you want to compress less, you throw out less of those singular values. So that's all there is. And then when we take that resulting matrix, we combine it back into a 2 4-dimensional matrices. And so it'll look like in this example, for example, this layer had 32 input channels, 64 output channels, and a kernel dimensions of 5 cross 5. But when we change it, we chose the middle dimension to be 42, what we call the rank. And so this layer ends up with 32 input channels and 42 output channels. And if you look at the kernel as well, the kernel also got decomposed. So it was a 5x5 kernel. In this case, it's a 5x1 kernel. And then the next layer has a 1x5 kernel. And if you see, like, the output channels here become the input channels over there. and the output channels from the original layer are the output channels coming out of this layer. So if you think about it, if you take these two decomposed layers as a whole, like in PyTorch, you can combine these layers into a sequential, for example. So if you take a sequential of these two layers using PyTorch terminology, then the input into this sequence of two layers is the same as the input that was there before, or the shape of the input is the same. The shape of the output going out is the same. It's just that this layer has been reduced into two smaller layers. Okay, so this is a very quick introduction to Spatial SVD. So, this is like, once we know how much to compress a layer, you can apply this technique and then you decompose the layer. And you can do this layer by layer as needed. So let's go back to talking about the compression ratio selection. How do we decide how much to compress each layer? And so there are two techniques that AIMET allows. And one of them is simply called manual compression ratio selection. So this is, as the name suggests, this is nothing. It's the user provides the compression ratios. So you would say, hey, this convolutional one layer, compress it by 40%. Layer 1.convolution2, compress it by 30%, so on and so forth. So now you would ask, like, where would you get the intuition to make the selection? And yeah, that is, I don't have a good answer for that. So what generally we would do, instead of like randomly making these choices out of nowhere, is we would apply an automatic technique, like in this case, the greedy compression ratio selection technique. And once we have applied that technique, we get a sort of, it has determined its, what it thinks is, this technique thinks is the compression ratios per layer, but that could be the starting point for somebody to now go and tweak it a little bit using, intuition that the model designer has. Okay, so this is fairly simple. So let's go to what this greedy compression ratio selection does. So let's take a look at that a little bit. Okay, so I'm gonna skip to this diagram over here. So the way the greedy rank selection does, as we know, what is coming in as a model, what goes out is a set of, essentially a compression ratio per layer, right? And so what happens in the middle is two steps. The first step is called per layer exploration. And what it produces is something called an evaluation dictionary. We'll take a look at that. And then given this evaluation dictionary, you do a greedy search. So we'll look at both of these steps. So let's look at the first step here, the per layer exploration. The per layer exploration is actually fairly simple. What it does is, let's say in this case, we have, as an example, a 4-layer model. So, and when I say 4-layer, I'm counting the convolutional layers over here. So let's say you have layer 1, layer 2, layer 3, layer 4, and then there may be other layers in there, like a batch norm ReLU. There may be other splits and element-wise adds and so on and so forth. So obviously this doesn't look like any model that you may be familiar with. It's just a toy model for it, just for the purpose of demonstrating this, what I'm trying to explain to you. So this per layer exploration, what it's going to do is it's going to start one by one through all the layers. So it starts with layer 1, and it's going to take it's going to compress it with a few candidate compression ratios. So in this case, by default, what AIMET would do is it would pick 10 candidate compression ratios. And these 10 candidate compression ratios are 0.1, which means the layer would be compressed down to 10% of the original. So it's like 90% compression, right? And so on and so forth, 0.2, 0.3, 0.4, 0.5, 0.6, and so on, all the way to 0.9. And then 1.0, which is essentially no compression, which is like a baseline compression. So we wouldn't consider that. So given these 10 candidates, or in this case 9 candidates, what it would do is it would take that layer, and for every one of these candidates, it would actually compress that layer, leaving all other layers the same. and it would, having compressed that layer to that target, it would do an evaluation of the entire model. Like it'll just run an eval, like an epoch of evaluation, and get us evaluation score, and it just notes it down in this table, and then keeps doing that for all the compression ratio candidates for this layer. Repeats it for layer 2, repeats it for layer 3, repeats it for layer 4, right? So you essentially get this table or a dictionary. Dictionary meaning, the dictionaries of first level is layers, like which layer you're talking about, and for each layer there is an evaluation score per compression ratio candidate. Okay, so now having this, after we have figured out this evaluation dictionary, you do something called a greedy search, and this is actually also very simple. So if you think of, in this particular example, I'm just showing 2 layers. We had 4 layers in the previous example, but let's take these 2 layers. So you would notice that what we are plotting here is like the evaluation score, which you could call accuracy, versus the compression ratio. So as we know, like the compression ratio means size of the compressed model, or number of max of the compressed model. Denominator is the original model. So high compression ratio numbers like 0.9 means little compression, like 10% compression, whereas low compression ratio numbers like 0.1 will mean high compression. And so you would see a pattern something like this, right? It won't be a nice smooth curve, but it would be, intuitively, the higher or the lower the compression, the higher the accuracy, and the higher the compression, the lower the accuracy. So you would see some curve like this. Generally, there's a knee in the curve somewhere. In some other layers, what you may see is that the knee occurs earlier. Okay, so in other words, if you think about it, this layer, a little bit of compression to this layer causes a drop in accuracy, whereas this layer can tolerate a fair bit of compression before it drops in accuracy. I mean, just comparing the two. So so this, I would call this a more compressible layer, and I would call this a less compressible layer. So what we want to do is, when we distribute the compression for the entire model across the layers, you want to pick a higher compression ratio for this layer and a lower compression ratio for this layer, right? So what we are going to do is, we are just simply going to think of a horizontal bar, a horizontal line going across these graphs, and we're going to just move this line up and down, and wherever it intersects this curve, we will, let's say we start in the middle, it intersects the curve at some point, we are going to find the corresponding compression ratio for layer 1 and corresponding compression ratio for layer 2. We add up all of this and we find, how much has the model compressed total as a whole. If it meets our desired compression, great, likely not on the first shot. So if it is, it hasn't met its compression yet, we move this horizontal bar lower. If it has overshot, we move the horizontal bar higher, and we can do a binary search and find this. So sounds somewhat like a naive approach, and I do agree that this is a fairly simple technique, simple scheme. However, in practice, it seems to work fairly good, and maybe somewhat surprisingly, but it does seem to work well across the set of models, at least, that we have tried to compress. So this is one of the techniques that AIMET uses. Okay, so having said that, let's jump into some coding examples. Actually, let me add one more thing before we jump into the code. So as you can see, that to compute this evaluation dictionary, let's say we had a model with 20 layers, and we do let's say 9 or let's say 10 candidates per layer. So that results in 200 candidates. And for each of these 200 spots in this table, for every one of these spots in the table, we have to run an evaluation, right? So this technique, though simple, actually can occupy a fair bit of like time, because it's just going to go through one by one and start evaluating, do a whole bunch of evaluations. So this is time intensive. So we have some tricks up the sleeve to help a little bit. So after we have like gone through the basic coding example, then we'll take a look at what we could do to alleviate some of this pain. So let me bring up my code editor over here. I start with an empty window, and I'm gonna borrow some of the code that we had used in the introductory video for doing spatial SVD. So let's start with some imports, and these are similar imports as what was already explained in the introductory video, so I'm going to skip over that. And here from Torch Vision, we took the Resonate 18 model, a pre-trained one, put it on CUDA, and it's ImageNet based model, so that's the shape of the input. So what I'm going to do next is I'm going to export this model before we do anything to Onyx. And the reason I want to do that is so we can look at the model, let's say in a tool like Netron, and then we can look at the model before compression and we can look at the model after compression. And so you want to do that before we do anything. So you'll notice like line number 17, there is this utility called Onyx Saver, which also comes with AIMET, and it has this functionality called set node names. So this is some syntactic sugar, or it's going to make that Onyx model a little better to look at. I'll explain to you when we look at it in Netron. Okay, so then let's go ahead and do our configuration parameters. And in the configuration parameters, we have the greedy selection. In this case, we have chosen the target compression ratio to be 0.8, so 20% compression. Just like in the first video, we're going to use auto mode, which is we are using greedy. And then, yeah, we're just basically saying that I'm going to choose auto mode over here. Okay, so then let's go ahead and call the compress model call itself. So to make it faster, I'm going to cut and paste some of the code here. So let's a very quick recap on the parameters: the model that we want to compress, the input shape, and evaluation callback, because we know that the greedy compression ratio selection algorithm is going to do a bunch of evaluations. So we want to pass an evaluation callback, the number of iterations you want to evaluate over. So by saying none, this is going to evaluate over all of the validation data set. And then we are saying we want to do spatial SVD compression. We want to target reducing max or multiply and accumulate. So essentially we want to reduce compute by 20%. Okay. And then the parameters. And there is this new parameter that we hadn't talked about in the first video. So this is going to show us some visualization. So I started a bokeh server, and this is the URL from the bokeh server that I'm feeding in here. And then when we look at it on a web browser, I'll explain to you what this is going to do. Okay, so after we have compressed the model, let's do a couple more steps. Let's print the model. So this compressed model call returns, you give it a model, it returns a compressed model, and it also returns some statistics. Let's print both of them so we see what it's doing. And also, like we discussed before, let's export out the compressed model now to Onyx. And I'm going to call this original model as Resonate 18 Onyx, and this one is called Resonate 18 SVD. And this is also going to set the node name. So what this is doing very briefly is if you export out the Onyx model using torch.onyx export, by default, the nodes within Onyx or the layers have no names. They have parameters which have names, but not the layers. And this is a sort of helper utility to set the names. It's a helper. It's not a simple helper. It's not a trivial job. But it basically tries to look at the Onyx graph, and it looks at the PyTorch graph and tries to match them up. Okay, so I'm going to run this code. Hopefully I copied everything correctly. I haven't typed, so I shouldn't have made a mistake. So I'm going to run this, and let's look at the output shows up on a different window here. So so it's doing something. So like I said, the greedy compression ratio selection, initially it involves creating an evaluation dictionary, and that is a very intensive effort. So it's going through its, I think what these logs are saying is it's going through its job. It's basically starting with the first layer, which is con1 in this Resonate 18 model. And it's starting with compression ratio 0.1, and then 0.2, and then 0.3, and so on. So essentially, if you remember, it's building up the table, right? It's building up this table. It's starting with the first layer and doing evaluation for 0.1, evaluation for 0.2, and so on. So it can get a little tedious to look at this log and figure out what's going on. So to make it a little simpler, remember we had the visualization URL we had specified. So we can bring up in a browser evaluation, and this is already connected. So let me show you. All of this is explained, by the way, on the user guide on how to set this up. But let me explain to you what it's showing. So here is a table. Looks a little bit like that table over there, right? I think it's a little swapped. So on your y-axis, if you may, or the rows are the layers, and the columns are the compression ratio candidates. So in this case, there are 10 or 9 compression ratio candidates and 15 layers. Okay, and it's if you see, notice that it has picked all the convolutional layers in the model, and it's going to, you can see like it's filling up the table. So one way to look at it is you see like a completion, like this is just for the evaluations table itself, or the evaluation dictionary, how much of that is filled. So you see like how much has it progressed, and you can also see it visually by looking at how much of the table is filled up. So let's take a look at this graph here, which is very interesting actually. So this graph, what it's plotting, it's like the evaluation scores or the accuracy on the y-axis, a very similar graph to what we had seen before. And then the x-axis are the compression ratios. So it's going to reset itself every time it goes to a new layer. So now it has started with layer 1.0.con2, which you can see over here. And it's going to start plotting the points. So it started with 0.1 and 0.2. It has found evaluation scores. This is not a, it's a linear scale, but it doesn't go all the way to 0. So it looks a little odd at the moment. But basically what you can see is you can see this graph that we had seen on the user guide, right? And as it keeps going, more and more compression or higher compression ratios, meaning less compression, the scores keep increasing, right? And you see sort of a curve like we had seen in the user guide. And if you'll notice, like the curve is not not necessarily smooth. It doesn't look very pristine, and that's the way most models are. There is a feature in AIMET which will smoothen this curve out, and the reason for smoothing out the curve would be to it'll help in the greedy search, that the one we looked at the very end. Okay, so this is a way for you to monitor what's going on and how much progress has been made, and you can sort of see the curves per layer. You can also plot these same curves later on at the end. So it gives you an intuition of which layers of your model are more compressible and which layers are less compressible. Some of it may be intuitive, some of it may be a surprise, but you can learn something out of this and either trust it to make the right judgment call in terms of how much to compress each layer, or start from that point and like tweak it and feed that in as a manual compression ratio selection. Okay, so since this is going to take a while, I'm going to pause here and wait for this this thing to finish. Some of you may have noticed that this is going rather quickly, meaning it's taking somewhere on the order of 9 seconds or so for each evaluation. It seems kind of interesting for ResNet 18 with ImageNet. So the reason it's relatively fast is because I'm cheating a little bit. So I've reduced the evaluation data set. Generally it's like 50,000 samples to something like 2,000 samples. So it's like 2 images per class. It still has the 1,000 classes instead of the 50 per class. And this, while this could be classified cheating, this could be a technique that you could use to speed up your evaluation dictionary creation, because perhaps it is not that important to get like the full high precision evaluation score. I think here in this case we are trying to see the trends, and maybe getting the absolute accurate score to the 5th decimal point is not what we are looking for here. We are looking for the trend. So I will with that I'll pause for a bit, meaning I'll pause the video, the run will continue, and I'll resume once this is finished. Hi, welcome back. So the compression has finished, and this is what it looks like at the end. So if you notice, I think it was trying to fill all this table. All the table is filled. I think I'd made a mistake earlier when I said there were 15 layers. It's a ResNet 18 model with 20 layers. Okay, so at the very end, it'll show you a chart like this. And what this is showing is each of these points represents one of those 20 layers. And it's showing how much it compressed each layer. So if you hover over it, it'll show you the layer name and you can tell how much it compressed. It may be hard for you to read, but trust me that it's going to show you the layer names. So what you can take out of this is the following. You see that some, like when it says 1, that means these layers were not compressed. So this greedy compression ratio selection algorithm decided to not compress certain layers, and other layers got compressed somewhat heavy, like this layer 4.1 con 2 got compressed 2.4, which means it got compressed like by 60%. And it's just the choices it made based on based on the explanation I'd given you in terms of what it's doing. So let's go back to look at the log that we were looking at, right? So if you remember, at the very end of our code, we had printed the compressed model, also printed the statistics, and then we had exported the model to Onyx. So let's start from the statistics a little bit. So zoom in a little bit. So what the statistics are showing, it's showing the same information that you saw in this chart over here in a table form. So it tells you, each layer, how much was it compressed, and some layers were not compressed at all, right? Also, let's also look at these overall statistics over here. So if you recall, we had asked it to do compression ratio of 0.8. It seems like it has, and for max, so it seems like it has overshot a little bit. So it has done, instead of 20% compression, it has done roughly 23% compression. And then the accuracy started out with 69.4 and has dropped to 67.2. And so this drop in accuracy you could recover back by doing a little bit of fine tuning, as we discussed before. And as we saw in the introductory video, fine tuning is nothing but calling your training pipeline. You have a compressed model. It's just like any other PyTorch model. You call your training pipeline and you're good to go. So this was the print of the model itself. So in PyTorch, when you print a model, it'll sort of pretty print the model for you. And what you can take out of this is you can see like wherever in the past would have been, for example, layer 2.0.con2 was a convolutional layer. Now it has been replaced with a sequential of 2 convolutional layers, right? And the same thing could also be visualized through Netron, through Onyx. Let me switch to that. So here's the ResNet 18 model before compression, and this is the model after compression. So if you see, basically you will see, like, take this first layer itself. This has been split into 2 layers over here after compression, and it started out with 3 cross 64, so 3 input channels, 64 output channels, and a 7 cross 7 kernel. And so if you see, like, it got split into 3, 11, 11, 64, and the 7 cross 7 kernel also was split into 7, 1, and 1, 7. I should click here, 1, 7, 1, and 1, 7. And so if you see, like, the shape of the tensor going out of here, that has not changed because that still has 64 channels. And the shape of the tensor coming in has not changed. So, but this, that 1 convolution got replaced with 2 convolutions, right? That's the main change. You can see that throughout this thing. So, yeah, again, motivation of showing this in Onyx is, this is like a regular PyTorch model. You can, export it to Onyx, take it to Target, or visualize it into tools like Netron. Okay, so when we looked at the code, we went over these parameters. So let me show you that you can also look at these parameters in the API guide. We had seen, like, right from the top of the user guide, you can reach the API guide at the very bottom of that page. Oops. Okay, so here's how you get to the API documentation, and then I browse down to the PyTorch compression APIs, and this is where you will see this compressed model routine that we have been calling with all the explanations for all the different parameters we have been passing it, like the cost metric, parameters for spatial SVD, and so on. So let's look a little bit closer at the spatial SVD parameters. So this was the mode. We either could select a manual mode or an auto mode. And we've been choosing the auto mode. In manual mode, you can just specify a list of module layer in PyTorch and the compression ratio. So a list of these pairs. In auto mode, we've been selecting greedy selection. There's also a second parameter, modules to ignore. We haven't looked at this, but in case there are certain layers that you have an intuition that shouldn't be touched, or after you run it once, you get an intuition that they shouldn't be touched. You can go in and put those into a list over here, and AIMET will pretty much ignore them, wouldn't consider them from the eval dictionary perspective, wouldn't consider them from a compression perspective. And then if we look at the greedy parameters itself, we've been using this target compression ratio. So let's look at some of the other things in here which are kind of interesting. So there is one for number of compression ratio candidates. So what this will control is if you saw the table, and we were always looking at these 9 different candidates per layer. So this, you can choose that number up or down using this field. So it's default 10. The 10th value is the compression ratio 1.0, which is the same as the baseline evaluation. So the evaluation is not repeated for that. So by default it's 10, but you can change it. So if you lower this number, your eval dictionary will get created faster, but you will lose resolution, because you have less number of candidates per layer. So certain layers, if you wanted to compress them down just a little bit, you will lose that resolution. So there's a trade-off to be made. Another parameter here is monotonic fit. This is turned off by default, but this is, if you saw that curve when we were plotting accuracy versus candidates for a particular layer, this will smoothen out that curve or make it monotonic. And then the last parameter, which is also very interesting from the perspective of speeding up eval dictionary creation for subsequent runs, is once you have created the eval dictionary, you can save it. It actually automatically saves itself into a .data directory as a pickle file, and so you can just simply take the path to that pickle file. You could like save it somewhere else if you wanted to, but you could provide that path to the pickle file in this parameter, and then it would simply skip over the eval dictionary creation, because you are giving it an eval dictionary, and it'll do the remaining steps. So this is very useful when you do an eval dictionary creation one time, but then you could try multiple different compression ratios. Like you could try with 0.8 and say, oh, this I could do a little bit more. You could try 0.7. You said, oh, this overshot from an accuracy perspective what I'm comfortable with, and you can come to 0.75. So you can try different compression ratios, final target compression ratios, but you don't have to take the hit of generating the eval dictionaries one more time, because it's exactly the same, right? The eval dictionary doesn't, the target compression only comes when you're searching through the eval dictionary. Creating the eval dictionaries it doesn't matter what the final compression ratio was. Yeah, I'm just trying to sort of both give you a feel of how you could browse through the API, but also from the API docs, but also giving you some hints on how you could like tune these parameters to have the to serve your purpose essentially. So I hope this video was useful for you. It's been a fairly long video. I anticipated something shorter than this, but I think there was a lot of stuff to cover. So we covered the spatial SVD model compression feature within AIMET, and we have also covered the greedy compression ratio selection mechanism. And I think we've gone in fair bit of detail in either of them. So thanks a lot for watching this video, and I hope it was useful. Please do see the remaining videos in this series of videos introducing the AIMET features. Thank you so much.